This video discusses the issue of maintaining stable frequency in microgrids under severe ramp rate disturbances. Consider an islanded microgrid having two main power sources, a PV plant and local generation. If the PV plant ramps up and down, the system load is transferred from and to the local generation. The question is, what will happen to the frequency stability of the microgrid? Here's what can happen if nothing is done to address frequency stability. Frequency, normally 60 Hz, can fall out of bounds if a ramped event is not addressed. The question this work addresses is, how long does a control system have to respond to the event and maintain stable operation? Before we answer that question, let's look at what solar irradiance ramps look like. Here is a 5-day recording shown in 1-second intervals. The top chart shows instantaneous irradiance. The bottom chart shows the change in this irradiance from second to second. Although the maximum change is about 300 watts per meter squared per second, it doesn't really tell you what the megawatts per second will be at the output of the PV plant. However, the data shown here can be used as a starting value that can be used to ramp down a PV plant. Here are two charts that show the impact of ramp rates on frequency decay. The top chart shows ramp rates varying from negative 10 megawatts per second to positive 10 megawatts per second. The bottom chart shows how the frequency is expected to change if no control action is taken. You can see that the ramp rate magnitude has an important effect on how much time there is to respond to the event. Another important parameter is a microgrid's inertia constant. Depending on the actual ramp rate, the frequency varies inversely proportional to the inertia constant as shown here. For this chart, we've assumed a system capacity of 10 MVA. So to maintain stable frequency, the deviation in per unit must be bounded by some preset value. This actual per unit value or percentage can be adjusted from the protection settings. If we solve the previous equation for the response time necessary to reach frequency bounds, we arrive at a quite complicated expression that estimates how long there is to respond to the event. The takeaway here is that the resulting expression is a function of the ramp rate, the inertia constant, and other system parameters. The importance of this expression is that it tells you how long the control system has before the frequency goes unstable. Knowing how long you have lets the control system take the best response at a given moment. Here's a pictorial representation of the previous equation. Consider that you have nearly 3 kilowatt hours of stored energy in your spinning generation. Under a ramped event of 2 megawatts per second, you would have approximately between 0.8 and 1 second to respond. If you had 4 or nearly 4 kilowatt hours of stored energy, your remaining time would increase to almost 1.2 seconds. The amount of energy stored in the rotors is directly proportional to the system's inertia constant and the system power capacity. In a more practical context, you would implement the previous calculation in a simulation or embedded in a controller. Consider a 15 megawatt islanded microgrid with a 10 megawatt PV plant and 7.2 megawatts of local generation. There is also a 1 megawatt PV plant, but this one is small compared to the other. Let's look at how a simulation would output the reaction time on the ramp disturbances occurring at the 10 megawatt PV plant. Considering an initial frequency of 1 per unit, at time equals 6, an event of 300 watts per meter squared per second starts to bring down the frequency. The remaining time calculator immediately outputs a value of about 0.7 seconds. This value is how long it will take for the system frequency to become unstable. As ramp rates are not actually constant, the remaining time starts to change as well. An increase in remaining time suggests that the ramp rate has reduced in magnitude. A remaining time of 0 indicates that there is no longer a ramped disturbance or that some control action has already restored frequency stability. As you see, the time calculator outputs a value that varies over time. It is then the responsibility of the control system to choose the right action based on the remaining time. A negative remaining time indicates how long ago the system went unstable. This work derived an approach to estimate the reaction time or remaining time available control systems have to respond under ramped events in microgrids. The contour chart gave a fast approximation that can be used to size PV plants, energy storage, and set latency constraints on control systems. Knowing how long there is to respond avoids repeating the same mitigating action every time there is a ramp, for instance, to discharge a battery or shed load. Knowing how much time you have lets the control action make better decisions based on the remaining time, and therefore can make your microgrid control system a lot smarter. Thank you.